Hello everyone. Today we'll be going over a reversing challenge from wolvctf. It's called Crack Me EXE. Shout out to the author Empty Bytes. Really cool challenge. And we have the description, a small file with simple premise. Surely there's nothing suspicious about it, right? And there's also a note. Depending on the antivirus EDR software you use, you may need to set up an exclusion for the executable. I'm not sure what this note actually means to say, but you know what? Let me just go to Windows Security or Windows Defender and disable that real-time protection just for this demonstration purpose. Yeah, let me boop. Let me do that, and that's out of the way. And I've already downloaded the file. Let's open up my terminal and clear it. So I've already installed the exe file. So in this case we are being given a PE32 executable. So P stands for portable executable. So it's the generic standard for Windows executable files. In case of Linux, you will be having the ELF, so that's for Linux. So in this case we have the PE executable, and you can't really use checksec on uh, let's say this particular file, because checksec is purely for Linux based things. And oops, see, yeah, so not an ELF file will be getting that. So checksec reveals all the permissions, like can we do the is the pi enabled, or the position independent executable enabled, or we can do a lot of other things with checksec. So in this case that is out of the way. Another thing to consider while looking at PE executable files is the way that they've been packed. So I can just do either exif tool. We don't really see anything special over here. Let's do strings, and okay, let me just do head. Okay, so the first thing, we have the generic, this program cannot be run in DOS mode. And the second is, we see in the third and fourth line we see something called UPX. So if we see what UPX is, so UPX is a packer for executables. So it reduces the file size of programs by around 50 to 70%, which is pretty nice. And there's another way that we can do this. So just open up your, there's another tool, I'll be showing this in a bit. Let me just pull that up. So you go to research and DEI. So DEI is okay, so DEI stands for detect it easy. So it's a pretty cool software that lets you or shows you what the packer that the executable has been packed with. So let's open up that and just put it in our executable and let it do the work. Okay, waiting for it to open. Yeah, it's okay, where it, okay, oh, it's already been initialized, but I can't really see it. Okay, so I'm not really sure what went wrong here. It's not opening. So that doesn't matter. Let's just go back to our terminal. So there's a lot of other ways to check if this has been packed with UPX. So UPX has an inbuilt utility in the terminal. So in this case I'm in my Kali, so or you can just do sudo apt install UPX, so that you can do uh, for testing the executable. You can do the use the T flag, and that gives you whether the challenge has been packed with UPX or not. In this case we have tested and we have been given the thumbs up symbol, so we are good to go. So you can you can decompress it by doing, okay, wait one second. You can use the so you can use the D flag Yeah, you can do the deflag to decompress the UPX files. So I've already done it. So I've used the command UPX tag d shell.exe and output it as unpack. So I've already done it. So you can see the unpacked executable file. The next thing that we do is we need a disassembler for reverse engineering. That's generally what we do. So let's open up IDA. So I've already done. So let me just no. Let me close these instances. Don't save database. And the other one too. Let's open up IDA. Yeah, let IDA open up. And you can start disassemble a new file. And you can choose your unpack.exe, which we've unpacked. And yeah, you can load resources, I guess, and click on OK. And yeah, so IDA does the job really well. And so in the left hand side of the section, you can see all the functions that IDA was able to disassemble. So we can go over to main, and we have this graphical representation of things. Like, it is really neat at what it does. And you can use F5 to disassemble or decompile and generate the pseudocode. So we have this fastcall. Okay, we have the main function. And basically what this entire pseudocode does is that, so first it initializes a lot of Windows API calls, or Windows, how do you exactly call it? It calls, I mean, so there's a lot of API calls that this executable does. So it's not exactly the word that I'm trying to put across, but it does a lot of dynamic API calls. And it retrieves the function addresses of the Windows API functions. For example, we have the open process, which opens up a new process, the virtual protect exe, the write process memory, the virtual alloc exe, and so on and so forth. So first it does a lot of initialization of these Windows API functions. And then we start off with the variable definitions. We have a bunch of int64 definitions, and then certain buffers. And then once again we initialize the DLL files. So so yeah, so basically till here we have all we have is dynamic API resolutions that going on. So this highly suggests that this program can be solved only with dynamic reverse engineering. So in reverse engineering we have two types. One is static and dynamic. Static is basically you have everything in front of your eyes, so you just need to reverse engineer as the opposite of whatever they did in the encryption. Dynamically refers to when the program has a lot of system calls that is been doing, and you need to use breakpoints. You need to run the exe file to actually figure out what it's actually doing. So till here it's just function calls. And then we have this little bit of a if loop that says that if debugger is present, it'll be giving out the nice try and exit. We can just try it out. Go to debugger and start process. Yes. And okay, so that happened in my others monitor. Wasn't able to see, but let me try to do that again. Okay, it's still on my other monitor, it's not getting visible here. Let me see what I can do. Okay, let's actually finish going over what this pseudocode of the main function actually does, and then I'll show you what happens if we actually attach a debugger to this executable. So let's do that. So and then after this, if the if loop, we have the memory allocations. We open up a process and assign some memory to it, and I'm not really that advanced in like really explaining all these stuff, and just learning out, and thought of recording my learnings. And then you will see over here we have bunch of um, we see some. Okay, okay, so this actually opens up a process and assigns some memory to it uh, with the usually the virtual alloc, virtual virtual alloc, yeah, using this. And then we have a couple of variable initializations. And okay, so this is where the juice of the pseudocode actually is. So this takes in this does an XOR encryption with random values using the strand function of a certain value, and then it XORs the bytes of this particular v9 with the values generated by the strand function, and stores it in the function or the memory location that has been initialized by the open process. So this is what it does. So XORs and stores it in the memory location assigned by the open process uh, instance. Okay, and then we start by injecting the data with the with usually this is done by write process memory, and we go on to some sort of now we go on to the actual output of the pseudocode. So it asks for the password, and once again it checks if we have a remote debugger present. If we have present, it just outputs no cheating and exits, another thing that we need to bypass. And then next we have uh, let's say it it read writes and basically compares whether the input that we've inputted is correct or not. So if it's correct, it says it's correct, and if it's not, just says not. So let's actually let me try to actually demonstrate what actually happens if we attach a debugger in this. One second. Okay, yeah, so we're back. So if we want to attach a debugger, let's just go on to the debugger tab and let's start process. And okay, that was probably too fast for you to see, but you saw the terminal that popped out, right? That gave you the nice try output. Let me try that again. Let's see. Yeah, you probably saw that right now. So that explains this particular loop. And there is also another remote debugger present. That's I'm not really sure uh, how to demonstrate that, but that is also another debugger check. It prints out the no cheating and it exits. So first and foremost, we need to um, so this is dynamic reverse engineering, right? So we need to bypass the the debugger the debugger check, and then we get on to the main function. So it opens up a process, assigns some memory, does the XOR encryption with the SRAM and all that, and then stores the memory location dynamically, and it asks for the password, and then checks whether the password that we've entered is right or not. So once all these out of the way, let's go on and let's try to dynamically reverse engineer this particular function. So another application that I've liked for this is x64 debugger. Let me quit this and open it up again. Okay, so you can't really open it here. let me go over resources, releases, and another x64, and here we have the application. Okay, you can do two things. Either you can open the exe file directly, or we can attach files here. Let's just open it up, and yeah, so this is actually what I won't be going over detail of what this actual interface actually looks like. So this is the memory location, this is the assembly code, this is certain register information. Okay, so this one is actually interesting. So it lists out as default x64 fast call. So fast call is a calling convention in Windows operating systems that basically makes a lot of system calls with all the arguments of the registers arguments. And so for each and every system call that you do, it shows you the arguments of the registers. So in this case, I'm not sure which instruction that we are in right now, but for that instruction we have RCX, RDX, R8, and R9. These are, and also the RSP plus 28. These are 5 arguments that we have that actually shows you the data that has been the argument that have been assigned in order to make that particular system call. So we can also you go in here and actually just a brief overview. So fast call calling conventions specifies that the arguments to functions are to be passed in registers when possible. So this applies only to the x64 architecture, which applies to us in this case. So pretty cool stuff. And another thing that I want to point out is you guys have to go and check out this particular um, Reddit blog. So it demystifying the CPU and x68. What is x64? I mean, there are a lot of architectures, and there's a lot of confusion among these stuff, including me. And this by far actually explains a lot of good stuff. Like it explains in a certain way that we understand. So another thing to check that out. And okay, back to x64. So we've opened up x64 debugger. For that, unpack exe, and we can also go to symbols, go to unpack exe, and look at what it's actually doing. Okay, so if you see here, this is actually running the exe file, because even though I've opened it, the x64 automatically saves the last session that I've been doing. You can just go and quit it, just stop it. And okay, so the objective that we are having right now, okay, so to bypass this is debugger present thing. So there is something called plugins in x64 debugger, which is really famous, and one of the most famous things is scyllahide. So scyllahide, let's just pull up scyllahide, and yeah, okay, so this is for latest. 1 second, wait, not this, yeah. So the scyllahide is a x64 debugger plugin. So it can able to, it has the ability to basically fake itself, fake the program into thinking that there is no debugger that's going on. So yeah, it can you can basically bypass anti-debugger checks. That's what it actually does. So we can pull that up. So you can, okay, the thing that I showed previously, this is actually x64 plugin manager. I find it really interesting, I mean really easy to use. So you just have to go to releases and download it, and it sort of gives you the plugin manager sort of things to, yeah, let's open that up. So it gives you all the plugins that are currently available and lets you install it by just one click. And the thing that you need to be aware of is the root directory, or options. Go to options. You guys have to set the root path correctly. I've had issues with these, and that explains this particular GitHub issues blog. And at the end, this person also configured the root directory of the plugin incorrectly, so you guys have to remember that. And you guys can open the scyllahide and you can install it. I've already installed it. Let me close that, and this should pop up in your x64 debugger application. So going under scyllahide, we have a couple of things. We have options, load profile, inject DLL, and the one that we have interested in right now, it's attach process. So this actually searches for process, or we have to enter the process ID in order to dynamically run the process under scyllahide. So this by default, by automatically bypasses the anti-debugger check and lets us do things. And another interesting thing is that you see this this sort of markers thing. So if you do this and drag it over here, you can see that it's already recognizing the executable as IDA, and it's really fun. Or you can go to Explorer, or so many different stuff. Like wherever you point this marker onto, it gives you the exe file of and the PID of that executable. So that's pretty cool. And there's no you can find out the executable. Let's actually run it first. Okay, so it asks for what's the password. We can just do, just for the first trials, of course, let's do subscribe. Let's do subscribe. Of course we are not subscribed. Let's run it again, and this time, to figure out what actually the process ID of this the running process is, we can just go on to IDA. Let's hit attach to process and let's search unpacked, and there we have it. The process ID is 12080. So that is our process ID, 12080. Yeah, so it also recognizes the exe. Let's attach it, and now we are in the actual exe file. Yeah, so we're in. So we see the open process stuff, and all the dynamic Windows API calls. So the next step is actually to set up breakpoints. So you can set up breakpoints by using selecting the instruction and pressing on F2, just F2 on and off. So you can set up F2 with that. So I've set up breakpoints in most Windows API calls to figure out what these API calls are actually doing. So that is our objective right now. So we can also see, if we scroll down, we see the nice try thing. So this is where the program actually exits if there is a debugger that's present. Let's try to run it once again and figure out if it's actually doing the things, if it's actually bypassing the debugger check. Let me reload it, and let's go on to, and we can this actually runs the debugger and runs it until the next breakpoint. Let's run it. Okay, so we are in the first breakpoint of the Windows API. So currently this opens up a process. So we have to keep in mind what these registers under the fastcall convention actually does. Moving on to the next. Okay, next. Okay, so now we are in the remote debugger check. It also bypasses that. Otherwise it would actually quit and exit out of the function. Otherwise the execution will be stopped. Moving on to the next. Okay, so right now we also bypass the nice try, uh, the debugger check, which is also nice. So scyllahide actually um, allows us to bypass these stuff. So now we are in another really the right process memory. So this particular instruction, let me this particular instruction call R12. So what it does is that, let me zoom out a bit. So this is where in IDA we are in this particular section right now. So we have done the XOR function, or all the mathematical functions. Okay, okay, we are in this particular spot right now. So we are writing to the memory location of this this pointer. So we can just rename global item to somewhat like encrypted bytes, just for our convention. So once again, going over the process, it opens up a process and writes uh, it writes to a certain memory location, and this particular v9 variable is the pointer that points to the memory location of the target process. So we are currently in that instruction right now. And if we look at some of the fast calls that we're doing, so we see that RCX, which has only C8, this shows this, actually I forgot. Okay, C8 stands for either the byte size, or and R9 is also 8B, which is also showing the, what do you say, the length, or the size, the total size of the encrypted bytes, the location. And R8 shows you the memory location of this particular of our R8 is basically showing you the memory location of this pointer. So let's go over to there, and you can right click and follow in dump. So let me expand this. So once we've followed this particular instruction, starts with 7FF and ends with 080 in dump. So you can see straight away that you can notice some sort of a flag that's going on, and it kind of gives you an idea of basically we are in the right direction. So overall, what we've done is we've set a breakpoint in the exact point where the memory location or the pointer is being assigned to that particular memory location. So in this case, it's this one, and you can right click and follow and dump. And then, okay, a little bit of a side note that I want to mention is that, so in this instruction, in this particular instruction that is actually writing to the memory location of the target process, so the R8 instruction or the R8 register is actually the pointer address. So this one that ends with 080 is the memory location of the pointer, and it's not of the target process. And the one that we are interested is RDX register. So this is actually the memory location of the target process. So if you follow this in dump, we'll be looking at it's all 00s, because I've not actually executed this file throughout, so it doesn't happen. But once you actually run it, so this is the target process that, or the location that we need to go. So that is just a little bit of a heads up that I forgot to do. Then the next thing that we'll be doing is, you can just go ahead and copy these stuff. Yeah, starting from the 808, you can just copy, go on to binary and save to file. So I've already done it, so I've named it dump.bin. So I've already done it. So let me open up my terminal. Yeah, so here is the dump and the exact same encrypted bytes in our terminal. So The next thing that we'll be doing is we have to further analyze what this dump actually is. So we can open up IDA again and open up the bin file in IDA. Not sure, my voice is getting cracked a lot, probably because it's Ramadan, I guess. Okay, so let's open up dump and basically click on OK. Let's go with 64 and yeah, okay, I guess. So we have just one function, so it automatically IDA automatically recognizes this is actually a function. So let's use F5 to decompile and get the pseudocode, and yeah, so this actually reaches the end of the function. So we have this particular function that we can reverse. So at first we are initializing some int64. So a bit about int64 integers in while reverse engineering these stuff is, so int64 stores it in big Indian format. So all these stuff, this right here is a big Indian integer, 64-bit integer. So we need to convert it to little Indian. So I'm getting confused as well, so let me Google it up. Big Indian. Yeah, so in big Indian refers to the byte or the whatever that is a byte system where the most significant bit, or the MSB, is stored at the lowest memory address. So this particular big Indian number, the MSB is stored in the last memory location. So it starts with 90 and then goes on to 79, 34, 43 and 71. And also we have another variable. This is actually an array, so it goes over from the 0th index to the 3rd index. And in this while loop we are iterating over, this is probably the key, and we have the XOR operation that's happening. So we are iterating the characters of each hex byte into with the particular key. So okay, another thing to notice is that this LL this LL actually means for programs to recognize that this is a valid int64 integer. Otherwise, in certain programs, this leads to the program thinking that it's actually 32-bit, and that can lead to overflow errors and other stuff that we don't want to face. So just a little bit of information over here, and then you can write a script. I've already done it. Let me pull that up. Okay, so we have the key. So the key which is the v6 variable, okay, the v8. So okay, you have to convert it to little Indian, and also this is in decimal. You guys have to convert it to hex. So I've converted it to hex, and all these the array, I've gathered them all in a single array, and basically iterating every single character in this array with the key, and do the XOR operation, of course, and basically print out the flag. Let's do that. And there we have it. This is the final flag of the solution of the challenge. And yeah, this particular demonstrations goes over a bit, not too deep into dynamic reverse engineering, but sort of gives you a rough idea on how can we actually approach challenges like these. And a final note is that, like, I am by no means a proper reference to someone who's actually willing to learn dynamic reverse engineering. It's just introduction sorts for someone with actually no idea, to figure out what's actually going on, to give them a map in their in their mind, and always go and explore by yourselves. And yeah, bye.